We talked about state feedback in a previous video, two previous videos, but we had to have access to the whole state vector. And the open loop system here needed to be controllable. That's still going to be the case. But what if we don't have direct access to the full state vector X? In fact, we'll say there's a C out here, and all we get is a single output Y. So we go back to single input, single output. So let's see here. So this is the configuration. What we get is the output Y, not the state variable, state vector X. We'll put this observer in here. We'll talk about that in a second. Its input is the output of this system. And this observer's output is X hat, which is its estimate of the state vector X. This X bar should be an X hat. And actually this U should feed into this observer. Now, if this would make sense here, kind of, the dynamics of the estimate should maybe match the dynamics of the original system. So it would have this type of control system. It's A and it's B. Actually, the same A and B. But if you did that, the error vector, the difference between the actual X and our estimate of it, would have the same dynamics as this original system, the original open loop system. And remember, this guy could even be unstable. So we don't want the same dynamics. In fact, if the original system's unstable, our error will go off to infinity. So what we're going to do is have sort of a mini feedback loop inside this observer. Here's what the feedback means. It's going to take its input Y and subtract off its estimate of Y and feed that back into the dynamics. So here's what its state equation looks like. Looks like this. And the L is a vector of constants, kind of like the K was for the state feedback. Inside here is an L. So dynamics of that pair will look like this, which gives us its own characteristic equation for just the observer. So much like we did with control feedback, to find the K, we can find this L to place the observer's poles where we want them, as long as the open loop system is observable. So we can calculate an L, much like we did for the controller K. Here's a quick example. Here's the open loop system again. Here's the output equation. Let's check if observable. We did this example before for state feedback. This is an unstable system. Let's check if it's observable first, and if it is, find that L. To check observability, we need to construct this observability matrix V. Its first row will be C, and its second row will be C times A. There's a formula for this we talked about in previous videos. C times A turns out to be 0, 1. There's our V. Its determinant is 1 minus 0 or 1. That's not 0, so yes, it's observable. Somebody must have told us to put the, what was the problem statement? Oh yeah, we want the poles at minus 10. It's going to have 2 poles. The observer is going to have 2 poles, same as the number of states. We want them both at minus 10. So here's what its characteristic equation. So we want that sort of mini closed loop equation inside the observer to have these poles or this characteristic equation. So to compute this left side, we need to do this product LC. There's what L is, there's what the C is, which came from here. So that's what LC looks like. This is what the determinant we need to take now that we added the LC to the original SI minus A. I'll multiply that out and again equate coefficients. So L1 plus 3, we want that to equal 20. And all this back here, we want it to equal 100. Two equations, two unknowns, L1 and L2, solve it so we can find the observer. It's much parallel to finding the feedback gain. But now you have, it's a kind of a more complicated system. It's going to have a total of 4 poles. A whole closed loop system is going to have 4 poles altogether. Here's sort of that mini feedback system, that's the observer. Here's the output of the observer, which is the estimated state variable. It goes back and we get that feedback, that state feedback gain K. And anyway, the poles of the whole closed loop system are just going to be a combination of those 2 sets of poles. Poles we placed for the control part and the poles we placed for the observer part. Anyway, that is the end of my control systems. I guess there's no more to say. Bye-bye. Done with controls 101. Classical and modern.